And we're going to be dealing with stretches. And stretches today will, I guess, take care of all of the parameters that we're going to need to work with. Now, I've given you a formula sheet, and at some point today, I'm going to draw your attention to the formula sheet, because I had told you initially when we talked about H and K, there is a template or a formula, but it contains other things. It contains H and K, but it also contains A and B, which we're going to learn about today. So everything that we have done with translations and reflections, we're now going to do with what are called stretches. So we have vertical stretches and horizontal stretches, and if you know enough information about the type and nature of stretch, you should be able to graph the resulting function. If you know the equation that you start off with and you have enough information about the type of stretch, you should be able to write the equation of the new function. It turns out there are going to be invariant points when you stretch functions from time to time, but not always. And mapping is always in play. You can always talk about what x comma y becomes in any type of transformation. So we have to go through some terminology, and sometimes terminology in mathematics doesn't match definitions that you typically think of in English, so keep that in mind. Translations and reflections are transformations that change basically where the graph is and which way it is, whether it's up or down or left or right, whether it's over here or over there, but they don't change the shape of the graph. If the graph has this shape, it's going to have that shape no matter what. Now, it may be backwards or it may be upside down and it may be in a different location, but you're going to have that shape. You're not going to have a shape that's, say, taller, or a shape that's narrower, or a shape that's wider, or a shape that's shorter. It's going to be that size. A stretch will change the shape. And although it's not important right now, I will tell you that the word stretch in mathematics does not mean making something bigger. It could be that it's making something bigger or it's making something smaller. Okay? We just used that word stretch for some reason. We used to use stretch if it got bigger and compression if it got larger or smaller, but we don't anymore. We just use stretch. So a stretch is a transformation that changes the shape of the object. And basically, stretches will make graphs bigger or smaller in a very loose way. Stretches can be horizontally, or they can be vertically applied, or they can be applied both horizontally and vertically. So what are vertical stretches? A vertical stretch happens if the graph becomes taller or shorter. So and when you think of the word tall and short, we're measuring things vertically. And if I say Larry Bird, who was a retired NBA player for, I think, the Boston Celtics, if I say Larry Bird is tall, you're not worried about his arm span or how wide apart his shoulders are or anything, or his shoe size. You're looking at how tall he is, what's the vertical distance from the bottom of his feet to the top of his head. If I say that a particular individual is relatively short, what I'm doing is I'm measuring a distance from the bottom of their feet to the top of their head. But whether we're talking about tall or short, we're talking about things that are measured vertically. So vertical stretches will make things taller or shorter. We have a number that we use to describe how much taller or how much shorter something becomes. And that number is called a stretch factor. So a vertical stretch factor determines whether the object gets taller or shorter, and it determines how much taller and how much shorter it becomes. One of the things to note is that a stretch factor is always positive. I have seen on exams sometimes people talk about a negative stretch factor, and I think it is confusing. And when the time comes where I can get into more detail about that, I certainly will. But for the time being, I would like you to think of a stretch factor as being positive only. And what I am telling you is that if the stretch factor is bigger than 1, the object gets taller. You can kind of think of the number 1 as 100%. So if I had a stretch factor of 2, that represents 200%, which means the new thing is going to be twice as tall. That's why it's called a stretch factor. If the stretch factor is 2, you multiply by 2 to get the new height. If the stretch factor is between 0 and 1, then it will become shorter. So for example, if the stretch factor is 0.5, that's like 50%. The new shape or image or whatever we're talking about will only be 50% as tall. Can we have a stretch factor of 1? Well, yes, but that doesn't change the shape of the object. Can we have a stretch factor of 0? Technically speaking, mathematically you can, but when you apply a stretch factor of 0 to something, it has no height anymore. It's just going to be a flat line. So that is a line that I hope gives you an appreciation for what I'm talking about with stretch factors. If I take this original shape, and this isn't in your notes, and I do that to it, I want you to notice from your perspective, and I'm not going to get out a ruler and do this, but if you measure the distance from left to right on the original shape, and you measure the distance from left to right on the new shape, it hasn't changed. What I've done is I've grabbed the top and the bottom of it, and I've pulled the top and the bottom away from each other, somehow maintaining the width. And that would be a vertical stretch. And I want you to note how I indicate that. You would put this, I think, on a written response, but you would also add more words to it. But I've got 2 arrows pointing away from each other. And by the way, the vertical stretch factor is 2 there. And I'm not going to move the ruler over, but if you measure the height of the original object and the height of the new object, the new one is twice as tall. Is that making sense? That 2? Okay. If I, on the other hand, take this original object and I do that to it, I squish it, which we used to call, I compress it. That's what we used to say. But I'm stretching it. Mathematics, stretch can be pulling things away from each other or pushing them towards each other. This would be a vertical stretch, but I want you to notice how I've indicated that with my arrows. Because those 2 arrows pointing towards each other tells me some important information. If I were to measure the height of both of these, I would discover, and you'd have to measure it, it might be an optical illusion from your perspective, but the height of the transform function is only about 33% the height of the original function. So the stretch factor is 1/3. We could do the same thing with horizontal. Horizontal stretches simply result in graphs becoming narrower or wider. And I think you know where this is going. The stretch factor is going to determine not only whether it gets narrower or wider, and it will also determine by what factor it does so. So the stretch factor again is a number between 0 and 1 or greater than 1. I want to make sure you don't get deceived by something here. In this diagram over here, we are talking about, in this line at the bottom of the screen, we're talking about vertical stretches, right? That line I've drawn has nothing to do with vertical or horizontal. It's just a number line, right? I don't want you looking at that and going, well, this is a horizontal line. What's he talking about with vertical stretch factors? This is just a number line, that's all. So we have the exact same number line for horizontal stretches. And if you have a stretch factor bigger than 1, then it gets wider. If you have a stretch factor between 0 and 1, it gets narrower. So this would be a stretch factor that's definitely bigger than 1. The height of the object has stayed the same, but I think it's 4. I think the horizontal stretch is by, oh, I'm wrong. A horizontal stretch is by a factor of 3. So if you measure the width of the original, the new one is going to be 3 times as wide. If on the other hand I do that, I think this is a 1/4, maybe a 1/5. I would say that that's a horizontal stretch by a factor of a 1/4. By the way, don't ever say this. Don't say it gets 4 times narrower. That's just not mathematically what we want to talk about. You want to say that it becomes 1/4 as wide. It becomes narrower by a factor of a 1/4. All right, so basically whether it's a horizontal or a vertical stretch, this is what's going on. We can talk about shrinking and growing. Okay, vertically stretch the function shown by a factor of 2. What's missing here, and you're never going to be told this, you have to know this, is when we stretch things, we stretch them relative to the axes. So if I stretch this vertically, I'm stretching it vertically relative to the x-axis. And what that factor of 2 means is that any point that's above the x-axis is going to be replotted twice as far above. And any point below the x-axis is going to be replotted twice as far below. So we're stretching it in terms of distances relative to the x-axis. If we start off with this point here, and I stretch it vertically relative to the x-axis, if it were above, it would become twice as far above. If it were below the x-axis, it would become twice as far below. So it doesn't move. It's invariant. The next point, on the other hand, is 2 above the x-axis. So if I stretch it by a factor of 2, it's going to be 4 above the x-axis. And then we can do the same thing we were doing yesterday in a systematic way, left to right. Let's start connecting the points and then moving on to the next point. This original point is 4 above the x-axis. If I stretch it vertically by a factor of 2, it will be 8 above. This one as well is 4 above, so it will be stretched to a distance of 8, and it will be above. The final point down here is 4 below. And if I stretch that twice as far away from the x-axis, it will still be below, but it will be down at -8. And if we've done our job fairly well, it should cross through 5 on the x-axis because that was an x-intercept. Even though I didn't put a point there, that was an x-intercept, so it should be invariant because it's neither above nor below the x-axis. So if you want, you can put that in there. Circling the invariant points, these would be invariant. You can make a little mental note here that the invariant points for a vertical stretch are the same as the invariant points for a vertical reflection. Right? They're x-intercepts. Second part of the warm-up, vertically stretch the same function by a factor of 1/4. Well, that means that every point that's above is going to become 1/4 the distance above that it was. So, for example, this is 2 above. I need to figure out what 1/4 of 2 is. 1/4 of 2 is 1/2. And then I can connect these. The next point is 4 above. 1/4 of 4 is 1. We can connect them. And believe me, I know that when we did reflections, many of you could just visually reflect the thing. Stretching is a little more complicated. I think you need a systematic approach, point to point. Keep going. And the final point is 4 below. Stretching it relative to the x-axis by 1/4, we'll put it 1 below. And if you connect these two, you should still get this invariant point at 5. So that's what it looks like. And circling the invariant points, they would be the x-intercepts. Again, I know it gets repetitive, but because they're neither above to get closer to the x-axis, nor are they below to get closer to the x-axis. They're on the x-axis. Where we're kind of going with this is I hope you can see that what's happened here is the y coordinate has been multiplied by 1/4. But if the y coordinate on those circled invariant points was 0, which it was, when you multiply 0 by 1/4, it's still 0. Similarly, I hope you can see that every y coordinate here has been multiplied by 2. but the y coordinates on the invariant points have values of 0. When I multiply 0 by 2, I still get 0. Incidentally, where we are eventually going with this, and it will be today, is we could have a reflection at the same time. We could have a vertical reflection followed by a stretch by a factor of 2 vertically, in which case the y coordinate would be multiplied by -2, because the negative is used to flip the y to the other side, and the 2 is used to stretch it. All right, let's take a look at the other 2 warm-ups, which deal with horizontal stretches. If we stretch this function, it's the same function, horizontally by a factor of 3/2. 3/2 is 1.5. By the way, I hate this method of writing fractions. It's a nightmare mathematically. But you should be able to understand that 3/2 is 1.5. So this point that I've highlighted here on the screen at -6 needs to be 1.5 times further away. Well, 1 times further away is at 6 for a distance. Another half of that will take me to 9. So I'm taking this distance of 6 and I'm multiplying by 3/2. And I'm just saying if you do that, you get 9. I'm going to take this distance, this horizontal distance here of 4, and I'm going to stretch that point away from the y-axis by a factor of 150%, 3/2. And that's going to put it over here at 6. And then I can connect them and move on to the next point. Well, the next point will be invariant. In fact, I can circle it right now as an invariant point. Because if we're stretching things away from the y-axis, which is necessary to stretch things horizontally, then what that means is anything to the left is going to get further away on the left. Anything to the right of the y-axis is going to go further away on the right. Anything on the y-axis will stay the same. So I can connect these. Moving on to the next point, this is 4 away from the x-axis. 1.5 times further away would take it to 6. And finally, this is 6 away. 1.5 times further away will take it to 9. So this is the function, and that's the area invariant point. Are we okay with this so far? This is just a warm-up, getting used to what it means to have stretch factors that are bigger than 1 or less than 1. Take a look at the final one. We're going to stretch this horizontally by a factor of 1/2. So this -6 will be half as far away from the vertical axis. This at -4 horizontally will be half as far away. Invariant, of course, because it is neither to the left nor the right. This point will be half away. Half away? Doesn't sound right. Unless you're talking about that actress. Anne Hathaway. Oh, come on. No? All right, fair enough. We can connect these 2 points. And this one will be half as far away, which will be at 3. And I can connect the points. And of course, there we go. And of course, we're asked to circle the invariant point, and there's one invariant point. Any questions with that warm-up? All right. So you do not need to do this. When you turn the page, it says put your calculator in this mode and follow these instructions. That would be if you were following along on video maybe, or you were trying to do this on your own. I have these graphs loaded up. So we're going to be looking at a function y equals sine of x, which is a function you're not familiar with, not really, in terms of a graph. And if you were to do this on your own, I'm telling you that you would need to put your calculator in degree mode, go into your window settings and use these numbers for your minimum and maximum values of x in your scale and your minimum and maximum values of y in the scale. But I've already entered this into a file here. The question is, if we compare y equals f of x, and I'm going to write y equals f of x right here in the middle. F of x is the sine of x. If we compare that original graph to all of these, what's the change in the original graph? Well, let's take a minute and write the equation of the transformed function for each of these four cases. And this is really simple. If I have y equals 2f of x, and f of x is sine x, this is just saying y equals 2 sine x. That's all it's saying. It's saying you're going to multiply the entire function by 2. This would mean we're going to multiply the function by 3. This would mean we're multiplying the function by a third. And this would mean we're multiplying the function by a half. And I could have set this up, this exploration, using any function in the universe. We could have used x squared. We could have used tangent of x. We could have used the base 3 logarithm of x, and some of these things you're not familiar with yet. I could have used any function. There we are. That is what y equals sine of x looks like. And I didn't put arrows on the end, but it continues to negative infinity and to positive infinity horizontally. And we call it a sinusoidal function or a periodic function or an oscillating function. It oscillates between 1 and -1 vertically. And it just keeps going up and down and up and down. It's a wave. And if I were to graph y equals 2 sine of x, and you can see the legend in the top corner, we can see with a little bit of thought that 2 sine of x is the result of taking sine of x and stretching things vertically by a factor of 2. That, for example, the pink function has a maximum value here of 1, whereas the blue, and I don't have blue on here, has a maximum value of 2. So the y coordinate has been doubled. If I were to take a look at the y coordinate here and compare it to the y coordinate on the blue function, the y coordinate on the blue function is twice as great, and it's below the x-axis. So what's happening is we're stretching vertically by a factor of 2. Let's see if that holds up for 3 sine of x. Is it the case that 3 sine of x has been stretched vertically by a factor of 3? Yes. What about 1/2 sine of x? Stretched vertically by a factor of a half? Yes. What about 1/3, which I've just entered as 0.3 repeating? Yes. So what do we conclude from this? Write a conclusion about how an original function is transformed if the original function is multiplied by a constant to get this. There is a vertical stretch by a factor of, now I want you to notice that this is a parameter. It's not h, it's not k, but it's a new parameter, a. And that dot means a multiplied by a factor of, I'm going to put the absolute value of a. And the reason is, if a is negative, there's a reflection and there's a vertical stretch. But when we talk about the stretch factor, if a is -4, I think it's better for a student to say, if a is -4, there is a vertical reflection across the x-axis, and there is a vertical stretch by a factor of 4. I think it's almost the height of laziness to say there's a vertical stretch by -4 and expect the marker to understand that you know there's a reflection. You should write it out. And that's it. And this would work with any function. You can play around on your calculator, you can invent a function and graph it, and then put a 2 in front of it and see what happens. It will be twice as tall. And so far, this is the same, everybody, as last year, when you learned about stretching x squared. And I don't, if you were in my Math 20 class, I did use the word stretch, but maybe if you were in other people's, they didn't. They just said it gets taller and narrower, or shorter and wider. Okay, but they were stretches. I hope you recall that last year you looked, and whether your teacher called this transformations of x squared or not, you looked at transformations like that. Does that ring a bell? Okay, I hope. Now, keep in mind that in this course, we would use H and K. All right. Nowhere last year did you talk about horizontal stretches, and there's a reason for that. It's too hard on a Math 20 student's brain. It's complicated enough getting used to this. So now what I'm telling you is when we get into horizontal stretches, it's going to be a little bit more difficult. There's something you really, if you think it's easy to stumble with some of the other stuff, it's very easy to stumble with what we're about to learn. So now, second part of the warm-up, I'll write the function again that we're starting off with. It's y equals sine of x. And we want to write the equation for y equals f of, I'm just going to adjust something here in what I've written. I'm going to write f of x equals sine of x just to be consistent with what's going on here. When I say y equals f of 2x, that means if f of x is sine x, f of 2x is sine of 2x. And this would be sine of 3x. I like to put that set of brackets around the 2x and 3x, although when we learn trig, you'll find that you don't need to sometimes. It's implied that it's there. And then f of 1/2 x would be sine of 1/2 x. And this would be y equals sine of 1/3 x. And again, I've lost my link for some reason, so let me see if I can get it back here. I think I did. There we go. So I'm going to put up sine of 2x. I hope everybody is guessing that it's going to be stretched horizontally because we're messing with x. But it does not get stretched by a factor of 2. It gets stretched by a factor of 1/2. If I take a look at the original function, which is in pink, and at the risk of offending your eyes, there it is, right? That's the original function. And to go through one complete wave of this, it's called the period of the function. We will learn about that in detail in one of our 2 trig units. But it's how far it takes to start repeating. And if you take a look at that, it repeats every 360 degrees. This has a period of 360 degrees. It starts here at 0 degrees, and then it hits 90, and 180, and 270, and 360, and then it's going to start to repeat. Right? This thing is going to continue. But when you take a look at the transformed function, and I think most of you can see this, but I'm just in case you can't, When you take a look at the transformed function, that's the period of the transformed function. It's only 180 degrees. And what it's like, everybody, is that somebody has put a barrier. Didn't do a fantastic job of drawing that second pink one. I just want to get it out of the way. Imagine that somebody has put a ceiling on this and a floor on this, and you've taken that pink graph and you've pushed it this way. You've made it narrower. I know it's not narrower like a parabola is narrower, but the horizontal distance between features has gotten smaller by a factor of a half. Another way to look at it is the distance from this peak to the next peak would be 360 on the pink one, but on the blue one, it's only going to be half of that. So what happens here, everybody, is this is stretched horizontally by a factor of a half. There's something I didn't write down in part one of this warm-up. My computer's really clunking away here. Is what actually happens, because I think it was obvious what happens. That's what happened with this function in part A. Would you agree? And this is what happened to this function. I'm doing abbreviating because we're just in teaching and learning mode right now. I don't care about marking. But if you're writing a written response question, you would use words. What's happening here is that's the stretch, and here, that's the stretch. Okay? And the thing I want to point out is that the number for vertical stretches, the number that you see in the equation is the stretch factor. Basically, if it's negative, we got to get rid of the negative. But the number in the equation is the stretch factor. But what's happening here is the number that's in the equation that you see in the equation is not the stretch factor. The reciprocal of it is. And we can certainly predict what's going to happen here. Now, I'm going to go back to my graph and turn off the sign of 2x. If this repeats every 360, and I stretch it by a factor of a third of 360 is 120, so it should repeat every 120. In other words, I should see 3 complete cycles in this distance on the right of the axis. And I do. And again, there's nothing special about this graph. You could use any graph. If I were to look at sine of 1/2 x, which is our next one, according to this, we would predict this. It should stretch horizontally by a factor of 2. So the pink graph, which is the original one, will get pulled apart, and it will be a very long, sweeping wave. And this one should be a horizontal stretch by a factor of 3. Well, here's the 0.5x, and you can see that it's twice as long in terms of the features. And here's the 1/3, and you can see that it's 3 times as long. I mean, you can't just obviously see it's 3. You'd have to look at the numbers on the scale and do some comparisons of horizontal distances. But that's what's happening. So what happens here is when you put a number in front of x, and now we have another parameter, b. When you put b in front of x, there's a horizontal stretch by a factor of 1 over the absolute value of b. And just be careful here. When I write 1 over the absolute value of b, I'm just saying the reciprocal, that's all. If b was 2/3, the stretch factor would be 3/2. And this is one that people will struggle with. You'll think you have it straight, and then you'll get it backwards. So vertical stretches. On the next page, I've just typed up a summary for you, which I'm going to go through briefly. A vertical stretch takes every point on the graph and multiplies the y coordinate by some number. As we saw in the warm-ups, if the y coordinate is 12 and I stretch things vertically by a factor of 2, the new y coordinate will be 24. It will be twice as far above the x-axis. If the original y coordinate was -4 and the stretch factor vertically is 2, it's going to become -8. And it doesn't matter what that stretch factor is, you are multiplying the y coordinate by that number, and you're not touching the x coordinate unless there's a vertical and a horizontal stretch. The parameter a is what's responsible for vertical stretches. It's also responsible for vertical reflections. What happens is the equation of the function changes from y equals f of x to y equals a f of x. The vertical stretch factor is equal to whatever the absolute value of a is. So all you have to do to go from the equation to the stretch factor is just ignore a negative. But that number is the stretch factor. We already know this, although yesterday I didn't say a is negative. But if the number in front of f of x is negative, a is negative, and there's a vertical reflection. And the mapping is that a x comma y maps to a x comma ay. Sorry, let me repeat that. The mapping in a vertical stretch and or reflection is that the y coordinate gets multiplied by a. And notice I don't have an absolute value around this a, because if a is negative, I want the negative to be included in the party. Y has to be multiplied by -1 to switch its sign, and it has to be stretched. And invariant points are x-intercepts. Horizontal stretches, the x coordinate of every point gets multiplied by the stretch factor. The y coordinate does not change. The parameter b is what we use for horizontal and vertical stretches, for horizontal stretches and horizontal reflections. The equation of the function changes from f of x to f of bx. You put a b in front of x. The stretch factor is found by reciprocating b and ignoring a negative if there is a negative there. If there is a negative, there's also a horizontal reflection. The mapping is this. The x coordinate gets multiplied by 1 over b. It gets multiplied by 1 over b to stretch x to whatever its new value needs to be, and to swap the sign on x to the opposite sign if b is negative. If b is negative, you need to include it in this mapping. And invariant points are y-intercepts because they are not affected by horizontal stretches. So now let's put this into practice. And this was a long process to get to here, but the rest of the lesson should be quick. I hope, despite a couple of my little fumbles today, I've laid the foundation well. So this first question says, if I have a function y equals f of x, and I stretch it vertically by a factor of 5, what's the equation of the function? It's that simple. That's it. Now, if I said the function was actually the base 2 logarithm of x, which means if I said f of x is the base 2 logarithm of x, which, I mean, I might as well just be inventing things right now. You've never seen this before, right? But it is a mathematical idea we'll learn about. If I said that, then the answer to this question would be the new function would be y equals 5, times the base 2 logarithm of x. That's all. If we knew the specific function, we would take 5 times it. What about if I horizontally stretch this original function by a factor of a quarter? Well, then the new function would be f of 4x. Because b, which is 4, and 1/4, which is the stretch factor, are reciprocals of each other. So be very careful here. This 1/4 is not b, it's the stretch factor. It happens to be a horizontal stretch factor. And this is not the stretch factor, it's b. And people will get them mixed up. Any questions with 1a or b? Okay. A vertical stretch by a factor of a quarter and a horizontal stretch by a factor of 5. Let me tell you, this would be a very basic multiple choice question. Well, the vertical stretch factor is a quarter, which means it has to be either this one or this one, because a vertical stretch factor is the number a that you see in the function. So you can knock these two out. The horizontal stretch factor is 5, which means b is 1/5, because b and the stretch factor are reciprocals of each other. Vertical reflection across the x-axis. Now, just to be clear here about something, I don't need to tell you it's a vertical reflection across the x-axis. Because if you're going to reflect across the x-axis, you ought to be able to say, well, things above go below, things below go above. So it's a vertical reflection. And what that tells you is that whatever a is, it will be negative. Now, there's a vertical stretch by a factor of 2, which means a is -2. The negative part accounts for the vertical reflection. The 2 part accounts for the vertical stretch. If there is a horizontal stretch by a factor of 1/3, then b is 3. And I make a mistake quite often, which is not to read every part of the question. You want to just make sure you didn't miss anything, like there's also a horizontal reflection. So now I'm going to, before we answer this, I'm going to ask you to look at your formula sheet. And I'm just going to lay a little bit more foundation for what we're going to be working on tomorrow. On your formula sheet, you'll notice that almost half of the formula sheet is populated with trigonometric things. There's a lot of trig in this course. On your formula sheet, near, well, I don't know, it's about 2/3 of the way down, I think, says general form of a transformed function. Y equals a f of bracket b bracket x minus h n bracket n bracket plus k. Let me write that down. We have y equals a f of bracket b, another set of brackets, x minus h, close all the brackets, plus k. In this question D, is there a horizontal translation? Is there a horizontal translation? No. That means that h is 0. Is there a vertical translation? No. That means k is 0. And if all that's happening are stretches and reflections, if I put 0 in for h and 0 in for k, this becomes the following. So all I'm going to do is put those numbers that we established for a and b, I'm going to put them in here. That's it. So I'm going to end up with y equals -2 f of 3x. Capiche? Are we okay with that? Any questions? Right? What happens to the graph of a function if I replace x with 3x? Well, first of all, I'm messing around with x, right? I'm changing x. So whatever happens is horizontal in nature. And since we're putting a number in front of x, it's a horizontal stretch. When we add or subtract a number from x, it's a horizontal shift. But when we multiply x by something, it's a stretch. This is going to be a stretch by a factor of 1/3 horizontally, because we're saying we're doing this. So b is 3. Since we're messing around with y here, there's a vertical stretch. Does anybody want to volunteer what you believe the vertical stretch factor is in example 2b? And I say it hesitantly like that because you might be wrong. You're probably going to be wrong. Now, after I've said that, you might not be wrong. Does anybody want to stick their neck out on the chopping block? And the stretch factor is 5/3. It's the reciprocal of this number. And I'm not having a stroke, okay? I'm thinking clearly. The stretch factor here is 5/3. Because if you take y equals f of x and I replace y with 3/5 y, my template, let me go back and show you the template. This is my template. It's y equals. And all of these rules we've established have been established around y equals. And this is not y equals. I need to multiply both sides by 5 to get rid of this over 5 and divide both sides by 3. So this is the function in the form y equals af of x. In other words, everybody, this 3/5 is not a, because it's not the number that f of x is being multiplied by. This is now a equals 5/3, which means it's a vertical stretch by a factor of 5/3. Now I have one final thing to say about this example. And it's that I'm giving you this example to help you appreciate that we don't have a different rule for horizontal stretches and vertical stretches. The vertical stretch factor, I'll start with horizontal actually. The horizontal stretch factor is the reciprocal of the number in front of x. The vertical stretch factor is the reciprocal of the number in front of y. It's just that we don't often see it like this. Somebody has already moved that 3/5 to the other side of the equation where it becomes the reciprocal. All right. What if we replace x with 1/6 x and y with 5/2 y? Well, we can certainly do this algebraically. This would be 5/2 y equals f of 1/6 x. If I rearrange it for y, which I want to do to get it into this form, it's going to be y equals 2/5 f of 1/6 x. We need to multiply both sides by 2 and divide both sides by 5. So there is a vertical stretch by a factor of 2/5. There is a horizontal stretch by a factor of 6. I'm not really sure we need to write this out in words. Again, if this were a part of a written response, you would use words. I'm not even sure I need to write it down. You should be able to say that there's a vertical reflection here because there's a negative in front of the function. You should understand that there is a vertical stretch by a factor of 1/2 because of the 1/2. And you should be able to say that there's a horizontal stretch by a third. So if I were to say to you, what is A? A is negative 1/2. What is B? B is 3. What does B do? B does this. What does A do? A does this. And this is, whatever you do, don't use this. It's just my shorthand. And it does that. Don't do this on a written response. That's just me being lazy and saying it reflects vertically. And example 4, write the equation of the image of y equals x squared after a horizontal stretch by a factor of 3. So what would B have for its value if there's a horizontal stretch by a factor of 3? Maddie? 1/3, the reciprocal of the stretch factor. So B is 1/3, which means y equals f of bx, which means y equals f of 1/3 x, which means y equals, in brackets, 1/3 of x, quantity squared. And we wouldn't leave it like that. We would recognize that since you're taking 1/3 times x, we can certainly square everything. When I square 1, I get 1 squared. When I square 3, 1 squared is 1, 3 squared is 9, and then x squared. So this is the equation of the function. And what if I take the absolute value of x and stretch it by a factor of 1/4 about the x-axis? Okay, so I'm thinking about this. The x-axis is here. If I stretch things by a factor of 1/4 relative to it, I'm talking about vertical changes. Things above will be 1/4 as far above. Things below will be 1/4 as far below. So this is related to A. There's a horizontal stretch by a factor of 2, which means B is 1/2. There's also a horizontal reflection, which means B has to be negative. If you put those numbers into this template, which, again, there's an H and a K in there, and tomorrow we're going to throw all these parameters in together. We're going to put those parameters in there. A is 1/4. And then B is negative 1/2. So we have this. And then we're going to use the fact that f of x equals the absolute value of x. So f of negative 1/2 x equals the absolute value of negative 1/2 x. We don't in this course worry about simplifying absolute value expressions because they're really tricky. So bottom line here, everybody, when you take a look at y equals a f of bx, A tells you two things. If A is negative, there's a vertical reflection. And whatever the absolute value of A is, that's a vertical stretch. B tells you two things. If B is negative, there's a horizontal reflection. And there is also a horizontal stretch by the reciprocal of the absolute value of B.